All right, so welcome to lesson 13. It is on related rates. And in a previous lesson, we learned the technique of implicit differentiation, and that technique uses chain rule, and that's the technique that we are going to be using in related rate problems, where things change with respect to time. Our learning objective is to use a problem-solving strategy and implicit differentiation to go ahead and solve related rate problems. Here are some recommended problems to try, and let's just start with this warm-up. So say y is implicitly defined as a function of x, meaning y depends on x. I want to differentiate both sides of this equation with respect to x. I'm going to take the derivative with respect to x of the left-hand side, and I'm going to take the derivative with respect to x of the right-hand side.
Right. But I'll defend some of the let's say...
Okay. The left-hand side is composed with terms. I see that addition here, so I'm going to take the derivative of x squared with respect to x first. That's 2x to the power of 1. And if you want, there is a chain rule right here, times the derivative of x with respect to x, which is just 1. The rate at which x changes with respect to itself is 1. You could put that in there if you wanted. Plus the derivative of y squared. Well, the derivative of y squared is 2y, but wait a second, y changes with respect to x. Y is a function of x. We need chain rule. We need to multiply by dy dx, or y prime if you want. I think we've got space. I'm going to use both notations. And the derivative of 25 is just 0. So 2x times 1 is just 2x, plus 2y times dy dx, an alternative notation is y prime if you prefer, equals 0. And we are done. We have successfully differentiated both sides of this equation with respect to x. Now in the next problem it looks identical, but the difference here is that both x and y are functions of t, and we're going to differentiate both sides with respect to t. Taking the derivative with respect to t, that's what that notation right there means, of the left-hand side equals the derivative of the right-hand side. Okay. Now the left-hand side again is composed of terms. I get to compartmentalize my thinking and just think of the derivative of x squared and then just think of the derivative of y squared separately. The derivative of x squared is 2x, chain rule, times x changes with respect to time, t for time. X is a function of time. I need to multiply by dx dt, or x prime if you prefer. Plus the derivative of y squared is 2y, chain rule, times dy dt is equal to derivative of 25 with respect to t is also 0. Sorry, someone's walking in. Sorry about that interruption. And an alternative notation here, if I want to use x prime instead of dx dt, I'm welcome to do so. I just need to know that it's the rate at which x changes with respect to time, because x is a function of time. Same thing if you want to use y prime instead of dy dt. All right, so the reason why we have these two problems juxtaposed to each other is sometimes people feel like, well, hey, when I did implicit differentiation, I took derivatives just like normal, but whenever I was taking derivative of y stuff, I always had to hit it with a y prime. And that's true because you are using chain rule. And now,
And going from this line,
all of a sudden, I'm having to hit everything with an x prime or a y prime. You really were doing that here originally, but x prime, the derivative of x with respect to x, is 1. But what's going to happen for us in our implicit differentiation, oh, I'm so sorry. What's going to happen for us in our related rate problems is that any time you have a variable that is changing over time, you're going to multiply by that thing's derivative right after. Okay?
yep, that is the